The Ariane 5 climbed through the equatorial air with flawless thrust, 4 satellites still tucked inside its fairing. At T plus 30 seconds, every screen in the Kourou control room glowed green. You wouldn't have heard a single alarm. The Vulcain main engine roared on schedule. The 2 solid boosters burned true. Flight controllers watched their displays with the quiet satisfaction of a maiden voyage going exactly to plan. But inside the rocket's inertial reference system, a piece of software from the older Ariane 4 was still running. It had worked perfectly on dozens of earlier flights. No one had thought to question it. That program was converting the rocket's horizontal velocity from a 64-bit number into a 16-bit integer. On Ariane 4, the velocity never grew large enough to matter. Ariane 5 flew much faster, and 32,767 was the absolute ceiling that 16 bits could hold. The rocket was already closing in. The Ariane 5 tore upward from Kourou, twin boosters pouring flame across the jungle canopy. Inside the control room, you'd have seen green traces climbing every console, altitude up, velocity building, path true. The flight looked perfect. It was perfect. But a program left over from Ariane 4 had already begun its work. That program ran the alignment calibration for the inertial reference system. On Ariane 4, it started before liftoff and shut down once the rocket rose. On Ariane 5, engineers kept it running. Safer that way, they figured. The software had flown dozens of times without fault. No one imagined harm from something just watching. Yet it wasn't just watching. Every cycle, it converted the rocket's horizontal velocity from a 64-bit floating point number into a 16-bit integer. Ariane 4 had never flown fast enough for this to matter. Ariane 5 was different. Its horizontal acceleration was unprecedented, digits feeding faster into that cramped conversion each second. At T plus 34 seconds, the velocity crossed 32,700. 267 counts remained before the 16-bit ceiling. The rocket tore through sky, oblivious, while inside both redundant computers, a silent countdown reached its final ticks. The conversion instruction queued again. No handler waited for overflow. The designers had assumed the value would never breach the limit. Now, with less than 2 seconds left, that assumption faced its test, and both computers carried the same flaw. Inside SRI-2, the alignment subroutine picked up a 64-bit number, horizontal speed. The value was enormous, far larger than anything Ariane 4 had ever produced. The instruction was simple: convert that vast number into a 16-bit signed integer. The most that space could hold was 32,767. The horizontal velocity had already blown past it. At T plus 36.7 seconds, the conversion ran. The number would not fit. The CPU threw an operand error. And here was the critical absence. The software had no handler for this error. None. The designers had never imagined this routine could fail, so they built no recovery path. The exception crashed through unchecked. SRI-2 shut down entirely. Half the rocket's guidance died in an instant. The flight computer reached for the backup. SRI-1 woke to take the reins. But SRI-1 ran identical software on identical hardware, and the same conversion was already queued in its memory, the same overflow waiting. The handover that should save the mission might instead double the failure in the very next millisecond. SRI-1 woke. It ran the same conversion on the same corrupted value. Same overflow, same exception with no handler to catch it. The backup died before it could speak. Both inertial systems gone in under a millisecond. The rocket flew blind now. No eyes, no compass, no memory of where it pointed. But the flight control computer didn't know this. It sat waiting for guidance data, and something arrived. The dead SRIs had started broadcasting diagnostic bit patterns, error codes meant for engineers on the ground, streams describing their own autopsies. The flight computer had never been taught to recognize a dead guidance unit. It had been built to trust. So it read the diagnostic garbage as flight commands. A pattern that meant, "I have failed," became tilt hard left. The computer prepared to correct a trajectory that didn't exist. And somewhere in the silence between two dead machines, a command began forming that would tear the rocket from the sky. The command went out. The Vulcane main engine nozzle swiveled hard to its limit. The two solid booster nozzles matched it, all three pointing the same wrong way. One moment the rocket flew straight, the next it fought a phantom lean born from misread error codes. The angle of attack spiked, 20 degrees more. Aerodynamic pressure piled onto the nose and flanks like a fist closing around a straw. The airframe groaned. It had been built to flex, but not like this, not a full-body wrench against the sky itself. Inside the control room, engineers stared at numbers they had never seen outside of simulation disasters. The stack began to buckle. Pieces of insulation tore away. A structural joint between stages started to fail. And still the nozzles drove their correction, obedient to a ghost instruction, while the self-destruct system armed for exactly this kind of flight sensed the breakup and prepared its own command. The rocket was tearing itself apart to obey a dead machine, and the sky offered no mercy. The aluminum skin along the first stage buckled like a crushed can. Propellant tanks split open, spilling liquid hydrogen and oxygen that never caught fire. No explosion, just tearing metal and the shriek of a structure coming apart. The stack separated at a weakened joint. The two solid boosters, still burning, ripped free and tumbled into separate arcs. At roughly 4 kilometers above the Atlantic, the automated self-destruct finished what the air itself had started. Explosive charges shredded the vehicle, scattering wreckage in a rain of twisted alloy. 4 cluster science satellites, years of design, hundreds of millions of dollars, the hopes of dozens of research teams fell into the same dark water. Europe's most ambitious rocket had lasted less than 40 seconds. The control room at Kourou went silent. Somewhere in millions of lines of code and cable, a single flaw had ordered its own death. The engineers who would find it did not yet know where to look. In the hours after the debris fell, engineers at the Guyana Space Center combed through telemetry. They hunted for a cause. They found it in a software module carried over from the smaller Ariane 4 rocket, code no one had rechecked for the new vehicle's faster, more powerful flight path. Inside that module, a 64-bit number tracking sideways speed was being crammed into a 16-bit slot. The most that slot could hold was 32,767. The Ariane 5 was flying much faster. The number spilled over. The computer, faced with a value it could not hold, threw an exception and died. The backup computer was the same. It failed the same way, milliseconds later. The alignment function causing this had no job after liftoff. It ran for 40 seconds only because Ariane 4 had needed it. No one had asked why it still ran. Jacques-Louis Lyons and his team published their findings in July 1996. The report became required reading in engineering schools across the world, yet the deeper question lingered. What truth about trust, reuse and blind faith does this disaster still teach us? The rocket did not explode. It was told to die. With both guidance computers offline, the flight control system received diagnostic noise, bit patterns it read as frantic commands. The solid booster nozzles swiveled hard. So did the Vulcane main engine. The angle of attack passed 20 degrees. Aerodynamic forces tore the 50-meter machine apart at 4 kilometers altitude. And the self-destruct system finished what the software had begun. All 4 cluster satellites fell with the debris into the mangrove swamps near Kourou. $500 million, a decade of work, gone in 39 seconds because a number was too large for its container. And because no one had asked whether code written for a smaller rocket still belonged in a larger one. The Inquiry Board report published that July now sits with every engineer who builds safety-critical systems, a quiet shield against the next oversight. The lesson is not about rockets. It is about the invisible weight of assumptions we carry forward without looking.